All right. Hello, everybody. So, I had some of you guys reach out to me and ask some questions regarding the chemistry in this class. How did it relate to the biology we were learning? And I agree with you guys. It's a lot that we go over right at the beginning. You might even mistaken this. You might think you're sitting in the wrong class based off just the first week alone because there's so much chemistry that we talk about. Um, and it can be a lot, especially if you haven't had a general chemistry background. It can be kind of hard to filter through the concepts and, kind of decipher what's not necessarily that things are more important than others, but there are some concepts that we talk about in the class that kind of carry forward with not just this material, but the entire series. It's stuff that you're going to see in 7B, 7C, and even if you go and take biochemistry, you'll find that these topics, you just kind of keep revisiting them over and over again, which kind of leads me to an analogy that I wanted to talk about. So, one way that I want you to think about this is to think about the chem and bio that you learn, kind of like two opponents in a tennis game or pickleball or ping pong or whatever game it may be, something where there's something that rallies back and forth, because it can be really discouraging at first to think, oh my gosh, I need to know all this chemistry before I can even start biology, and that's just absolutely not the case. The nice thing about this is that you learn and acquire knowledge. So if you think of the ball that's being rallied back and forth, you have the two topics. As you go back and forth between the two, you're kind of going to come back with something new each time you go back and forth. And that's going to help solidify your knowledge. You're going to have a better, deeper understanding of things, and it's going to increase your confidence. And again, you don't have to know all of chemistry before bio or vice versa. It's just a game of going back and forth and building up your knowledge. And once you do it enough times, just like about anything else in life, you get pretty good at it. So that's just a word that I wanted to put out here. So please don't feel discouraged. I know it's a lot, but again, if you stick with it, it's going to stick with you. All right. So one of the first concepts I wanted to talk about was the anatomy of an atom, and I know that a lot of us already are very familiar with this. However, I think it's important to know that there's kind of different mental maps and mental models that you can have in your head when applying certain concepts. So I think for a lot of us, we know that, we think of an atom, we know the nucleus is made of these protons and neutrons, and then around it are these little spinning things called electrons. And that is true. However, there's certain models that I think are better than others for certain scenarios. And in this case, I think it's good that we think of not the electron space as just a thing where an electron's going around, but kind of like as a cloud here. It's like a mist or like a haze. So this electron is moving very, very quickly. And it could be here, and then it could be here, and then it could be moving here. And eventually, over time, if you were to watch the electron occupy that space, it would eventually make this haze. And this is kind of a better idea because this haze is like a magnetic field that is going to be, again, applicable for concepts later on of like how we think about space and shapes and things. I think it's just important to go over this quickly because it can be really deceiving. It's like three basic things you learn about, protons, neutrons, and electrons. But I mean, it makes up like all of the universe. And there are, people that go and spend years and, their entire lives just studying this stuff. And I don't know, it's fascinating to me that, these three little things can just have so many different like reactions and mechanisms and things in place. All right. So, a big thing that I had a lot of you guys reach out to me was asking questions about the different kinds of bonds that exist. So, within atoms and molecules and the way they interact, we categorize the different types of bonds and interactions that happen. And we have ionic bonds, we have covalent bonds, we have a thing called hydrogen bonding. We have a bunch of different interactions that happen between these molecules on different, magnitudes and different kinds of powers and forces. And we categorize that. So one of the big ones is a thing called ionic bonds. Now I know that we had talked about the octet rule and the fact that atoms have a desire to be stable, to reach a level of stability, more stable than whatever state that they're currently at. And one of the things that they can do is fill out their octets. So take the octet with a grain of salt. There's a lot of different ways that we've talked about how these are valence electrons, the outermost electrons of an atom. Um, but the octet works very well for a lot of organic kind of reactions and molecules that we talk about. So that's why it's relevant to biology. So in this example here, we have a sodium atom and we have a fluorine atom. And we can see that we can like look at their valence shells, and we see that sodium has this just this one lone electron right there. And then the fluorine shell has a space where it just needs the one more, right? So this sodium and fluorine atom kind of have an exchange that can happen among themselves that's a mutual benefit. And that is sodium saying, hey, I have this big valence shell that's unstable. I need seven more electrons if I want it to be filled. Fluorine's like, hey, I got seven electrons in my shell and I just need one more to be filled. How about I take that off your hands? So that is what happens. So they have an exchange, and then you get things formed that are called ions. So now that we have these ions that exist, and we'll see now that the sodium atom lost its outermost shell, and it gave up that electron, and it has a full valence shell underneath it. And now this fluorine atom gained that electron, and it was able to fill its valence shell. So because of that, these atoms became ions. And it's important to remember that ions can be positive or negative, and we have a different way to name them. So we have cations are positive and anions are negative. A good little way that I've always remembered it, that I learned from one of my professors a long time ago, was that cation is positive because cats have paws. So that's just a little way to remember the difference there. But important to know that ions can both be positive and negative, and that these ions are attracted to one another because of their the difference in their charges. So they stick together, and that is what creates an ionic bond. All right, so the next kind of bond that we're going to talk about is a covalent bond. So covalent bonds are different, and it's kind of in the name. You can think of as cooperation, co-player, working together. Um, and the reason for this is that this ionic bond was kind of an ideal situation where the sodium happened to have just the extra electron that fluorine needed, um, and that it would help both of them reach stability, right? Whereas that might not always be the case. Some instances you might only have atoms that exist like this, like a bunch of fluorines that are together. So, there's no sodium for that ideal exchange. So instead, what can happen is we can have this fluorine here and the other fluorine. They both need that missing electron, and this fluorine can go to this one and say, hey, I need something that you don't have, and you also need something that I don't have necessarily. But what we could do is we can't just get an electron out of thin air, but we could share one. So if I take this electron and add it here, and you take this electron and put it here, and we don't necessarily, again, we're not exchanging them, but what we're doing is sharing them, then we can create something like the example below, where we kind of have our octets being somewhat occupied as long as we stick together. So the way you can think about this, and this is why I thought it was good earlier to think of it more like a cloud, is that you have that electron space now that's being shared between the two atoms here. So now you have an equal amount of electron cloud density that is going back and forth between these. So while it's not an ideal exchange like this example up here, it still is beneficial. So it's an incentive for these two atoms to join together, and that's what creates that covalent bond right in the middle. That is mutually beneficial for both of them. It's to have more stability. So it's really important to understand that this bottom level here is much more stable than just them floating around being on their own. Okay, so now this is starting to get to the realm where I think conceptually it can get a little bit more abstract and difficult to grasp because we're starting to build upon layers of knowledge that we've learned previously. So in this example, I know I had mentioned I had this like handshake picture here, right? Where it's like an agreement between the two fluorine atoms, like, hey, it's beneficial for both of us to share the electron and come together and join this bond instead of, it's like as much as this fluorine's like, hey, I would like to have your electron and, leave you without anything. I can't do that. So we have to come together and like that's like an agreement, right? And I had this handshake here. And that is the case. But there are some atoms that are much stronger than others in terms of keeping the electron density and cloud around. So that's why I had it more here with a photo of like arm wrestling. So this fluorine, we learned about the electronegativity, and fluorine is the most electronegative atom. It really wants that last electron, and it has a dense amount of protons in the middle of it, compared to something like hydrogen, especially where there is so much incentive for that electron to go and spend most of its time with fluorine if they were to bond. So this is the same thing where they are looking at one another and they're like, "Hey, you've got something that I wish like I could take off you entirely, but I can't. So let's have an agreement, a handshake that will come together and form a bond." And this here is a covalent bond because again they're sharing this. However, is the big part is that the sharing is not necessarily equal. So while this hydrogen is having the satisfaction of having its orbital full of the electrons it needs, it's not necessarily even. So this fluorine is just the middle of this is just so electronically dense, or sorry, just so dense that the electrons are really going to want to spend a lot of time around here, around this fluorine, and not much time around the hydrogen. So it's only going to be. Let me see if I can make that a little bit darker. So it's still the electron's still spending time around this hydrogen. However, most of the time is spent in this fluorine, and that's going to be a very important topic for what we go on to talk about next. Now we're going to introduce two new concepts called hydrogen bonding and polarity. And I'm kind of going to weave back and forth between these two. So we're going to talk again about the covalent bonds that can be formed. So here in this example, instead of fluorine, we have oxygen. And for its octet, we know that it needs two more electrons here, right? And if there's two hydrogens that are nearby, they can bond. And I believe we all know that when that happens, when an oxygen forms with two hydrogens, we get a water molecule that exists. Now, this is where this concept, again, I'm really going to try to, hammer this in, is that the difference in the electronegativity between the hydrogen and the oxygen it's much greater for the oxygen to be much more electronegative. So it's important to remember that these electrons that are going to come and share the space from the hydrogen over to the oxygen are going to spend much more of their time hovering around the oxygen atom itself due to it being so much more electronegative. So just to go back to this example, the fluorine is very electronegatively dense. So that cloud, that mist, that haze is going to spend most of its time around that fluorine and not as much time around that hydrogen. Um, and we see that here with the hydrogen bonding that's going to happen with this oxygen, where it's going to come together to make water. And again, I try to represent it here of this haze that you have, where a lot of the density is up here at the top by the oxygen, and there's not as much density and cloud around these hydrogens. And as we know, by just looking at the periodic table, the hydrogen atom is just, one proton and one electron. So if there is, it's sharing its electron with the oxygen, if there's no other electrons floating around and that electron is just kind of spending a lot of its time over by the hydrogen, or sorry, my bad, over up by the oxygen, then that leaves this proton of the hydrogen exposed. And we know that protons have a positive charge, right? So that's where we can start to think of this polarity in this water molecule existing, kind of like a magnet. So we have this upper area here that's a negative because the electrons are spending all their time there. And then we have this positive area that's exposed because the hydrogen atoms um, do not have that protective shell anymore of that electron always floating around. So now that proton, that nucleus, is being exposed, and that's going to allow this to have this, we call it polarity. You think of like the North Pole. You have the North and South Pole, negative and positive, and the reason for something being polar is again because it has polarity. It has different ends of something, right? And we're going to talk about this later on too. When something is non-polar, it means that there's no specific specified favorable space for something to be positive or negative. It's kind of a universal dispersion. So an example I can give that really quick is like these two fluorines coming together. That's a nonpolar molecule because there's no positive and negative because this dispersion of the electron cloud is equal. There's no difference, right? It's a kind of an equal handshake. Whereas when you have this uneven like arm wrestling, and this fluorine's like, okay, I really want that electron. I'm going to take all of it over here. It leaves that hydrogen exposed. So this is going to be a like positive area where that proton is, and that's going to create what we call polarity. All right, so I hope I haven't lost any of you guys yet. If I have, please feel free to reach out to me on Discord, and I'm more than happy to jump on a call and try to explain this better. Um, so now we kind of have an understanding now, right, of like what polarity is, how it forms, right? We have to know, okay, how does something become polar? And we know it's because of that cloud, that density. Where is the electron most of the time? Um, so now that we know that, and we know like a water molecule has kind of a positive and negative end, we can ask ourselves, well, what happens when there's multiple water molecules, right? Because like most of the time when we look over at water or something, there's billions and trillions of little molecules moving around together that are interacting. So in this space, when we have a bunch of and my apologies that these aren't all exactly the same size, but the idea here is that you have a bunch of these water molecules all kind of moving and going around over each other and stuff, and they have those positive and negative ends, right? So you're going to have cases where here we have this negative end and we have this positive end of the other water molecule, and they're going to be attracted to one another, right? So that is where we get something called hydrogen bonding. So we have this negative end where all this electron density is, that is a negative charge or slightly negative, that's attracted to this positive region of the hydrogen. And I should note that these are not like ion charges. They're not as strong. They're slightly, which I could denote by this little like sigma here. So you're going to see that a bit where you're going to have like something like this or like this, and that just means slightly. And that's what all these different positive and negatives are. They're small little forces, and but they're still forces that are at play. They're not as strong as the cations and anions, but they are enough to attract the opposite ends of the water molecules and whatnot to each other. And this is just one example of hydrogen bonding. You can have many different kinds of molecules that are capable of hydrogen bonding, and we'll get to that in a bit. All right, so now we're going to talk a bit more about hydrogen bonding, and I think this is one of the really big parts that people start to get mixed up about. And it's very important to know that Not all hydrogens are capable of hydrogen bonding depending on what atom or other molecule they're attached to. Very, very important concept to know. That yes, hydrogen bonding is a thing, and certain hydrogens are capable of this characteristic. However, it's dependent on what atom they're connected to. So in this case, the electronegativity between hydrogen and carbon is negligible. There's not that much difference. So di- there's not really a strong preference for the electron to hang around the carbon more than the hydrogen. And because of this, we get this even dispersion. So you see this cloud, and that's why I kept using this. I keep using this cloud analogy, is that if you were to let time go and you were to take a bunch of little snapshots over and over where the electron was at any given time, you would see kind of an equal dispersion. There's not really a specific spot that it wants to hang around. And because of this, you have something that's neutral. And this right here, we would categorize as non-polar. So again, we know that polarity, again, polar, think of that word. We have like the North Pole, South Pole. We have attractions, we have forces, we have a positive and a negative. In this case, we don't have neither. So it's not like, don't think of polar as like something that's positive and non-polar as something that's negative. It's not like that. The concept is more of if there is a charge or not. And in this case, when you have something that's non-polar, it means that there's no charge. It's like equal distribution. And that's also something that we'll talk about later that I think can trip a lot of people up. So, again, just really want to emphasize this point here that this hydrogen attached to this carbon, like this one here to this, is not doing hydrogen bonding because there's an equal dispersion here. So this hydrogen still has its proton there, right? But it's not exposed like it was in the example with water, where these hydrogens, when they're attached to the oxygen, that's very electronegative and wants that electron to be more around it than the other atoms, then you have this hydrogen that's exposed. And in this case, it's not. So again, that's that neutral, no charge, not polar. Moving on, I know that I said that the atom is the molecule may be capable of hydrogen bonding depending on what the hydrogen is attached to. So in this case, this is a really good example because we have instances where the hydrogen atom is capable of hydrogen bonding on certain parts of the molecule, but not others. So again, you have like this hydrogen and carbon here, they have an equal electronegativity. So they don't really have a preference, the electron doesn't really have a preference for where it wants to be. But you have something like this, you have something like here with this oxygen and hydrogen, and they they have enough of an electronegativity difference where that oxygen wants to hang out, sorry, that electron wants to hang out more around that oxygen than it does the hydrogen, and that's going to lead to this uh, slightly positive charge here, and then this slightly negative charge here for the oxygen. And I know this density thing. I kind of have it for both of these as negative and positive. I wanted to have this different from this in terms of just showing there's a difference in the electron density where this is an unequal distribution and this is an even distribution. Um, so we can think of that kind of that magnet example again that we were talking about earlier, where we had like a positive and then minus on here. We have most of this is neutral, right? However, we have an area here where this oxygen is going to be, because of its electronegativity and wanting to have more of the electrons around it more often than not, this spot's going to be kind of slightly negative, and then this spot here is going to be slightly positive. All right. How are we feeling so far? I know this is a lot. There's so many different topics. And again, just remember that tennis analogy, ping pong, it's going to go back and forth and eventually it's going to stick. I promise. It takes a while and it takes a bit to get down these different concepts. However, like I promise that it does ultimately, it will make sense if it doesn't already. And again, please feel free to reach out to me at any time. So now I wanted to take that knowledge that we've talked about and now apply it to biology. So I was going to do something a little more practical and take this knowledge and apply it to stuff that we've been talking about. So now that we kind of have that fundamental chemistry knowledge, we can take some actual biochemistry stuff and start applying like what we know. So, in this example here, and I apologize, it's not the cleanest drawing. There's a carbon chain with a bunch of hydrogens, and then at the top here is this phosphate group. Um, and you may know this. We've talked about it. It is a phospholipid. So here we know that phospholipids are amphipathic, right? I believe Yao has talked about that, where it means that one end is polar and one end is non-polar. That polarity difference exists, um, and that is crucial for understanding why life is able to exist in the way that it does, that we know it as. All right, so this is where things get pretty fun, at least in my opinion. So now that we have those concepts that we have of chemistry, we can again apply it to like how we understand parts of life. And now we kind of, because of polarity, we can kind of get an idea of how life started to come to be. So again, we have these organic molecules called phospholipids. And by themselves, again, they're amphipathic. They have a non-polar end and they have these polar heads, right? So we know that polar is hydrophilic, meaning it likes water. Now, we haven't talked about that yet in this lesson, but I know we've talked about it in the lectures. You know, hydrophilic is hydro being water, philic meaning loving. So, a hydrophilic head means that it loves water. And why does it love water? Well, we know that when we talked about water earlier, we talked about water having polarity, right? So, water has these positive and minus like little charges, and other molecules that are hydrophilic just mean that they're attracted to water. So it means that they're molecules that are capable of having attraction. Where we have again the amphipathic molecule here of this phospholipid, these fatty tails. They don't have a charge. They don't have a preference. They're neutral. They don't really have a say in any of this. They don't they're not attracted to water, but water is not attracted to them like at all because of the because water has the charges. So what water does like is the positive or negative charges that exist, and in this case, the electron density that you have at these phospholipid heads. So you have these water molecules that like this area, and they don't like this nonpolar region because again, there's just a neutral, like no negative charge. So what is going to happen if you have a bunch of these phospholipids just floating in the water? Well, you're going to see something like this, where you have these the inner layer, or the inside, the lipids form and kind of stick together and group together because they're being pushed into this because of the properties of the water being um, eh, attracted to the phospholipid heads. So again, these outer heads are going to want to all like reach out and face the water, and the inside is not going to. And that's how you start to see something like this barrier that exists. Now, what's really cool is that if you keep going, if you have a bunch of these phospholipids, you can get an interesting scenario where what we talked about, the phospholipid bilayer, bi being two. So we have two layers of things. And this case being two layers of phospholipids, where you have these hydrophilic heads that are attracted to the water on the outside. And then you have the non-polar tails that want to all group together. And then if you have that go on enough, you can have the another side where you're going to have that phosphate head again that's going to be attracted to water. And just use your imagination here for a second. But if you imagine this being a wall that eventually curves and goes all the way around, eventually you'd have a giant ring, and within that ring, uh, you would have a separation of two different of water in the inside and water on the outside. And while in this example, it's just water for the time being, it allows there to be a possibility where the water inside could be a different environment than what's on the outside. And that is like one of the main building points, one of the main things for how life came to be, and the fact that this amphipathic things can exist, and that we can have things like these bilayers. So we are mostly made of water. Cells are mostly made of water. um, and the difference is though is the what's going on in these watery environments from the outside and inside. And that's really where you get um, this amazing thing and these interactions. And again, this is all because of polarity and the different kinds of bonds that exist. So I hope it's starting to click a bit. We just have a little bit more to go to. But again, if you guys have any questions, please feel free to reach out. All right, so the last topic we have to talk about, we've talked about ionic bonding, covalent bonding, hydrogen bonding. The other one is these tiny, small little things called van der Waals forces, or London dispersion forces. One way that I remember this is that the secondary name London, these are weak, very small. So the song "London Bridge is Falling Down." So if they think of that, it's that something weak. So anyways, the van der Waals forces are just nowhere near as strong as ionic or covalent or hydrogen bonds. And one thing I do want to talk about really quick that I forgot to mention earlier is covalent bonds are very, very hard to break because they have that agreement, right? And they have that that mutual understanding that are like, okay, I need your electron, you also need my electron, like, but we both like it because we're stable, we don't want to give it up. Ionic bonds are much easier to break, hence like why when you put sodium chloride in water, it disperses very easily, because they already kind of have like what they need. Whereas these covalent bonds are very strong and very hard to break, and it releases a lot of chemical energy when they are broken. um, we can talk about that later at another time, but that's part of the reason why like ATP is such a good molecule for powering our body and whatnot. So back to the London stuff. So again, really want to emphasize these forces are very tiny. There's not really too much you need to know about them aside from them just being weak little interactions that happen here or there. So in this example, I have this, and for simplicity, it's just like chain of carbons, but you can assume that hydrogens are hanging off of it. Again, we have this equal dispersion of electrons, this cloud, right? It has no preference for where it wants to be exactly. But if I were for a moment to take something like a magnet with a positive end and put it towards this molecule, the electron cloud would shift towards that magnet, right? And then it would expose the one side where all the protons are, right? And it would leave it slightly positive. And because of that, you have a induced dipole. This is a part of the van der Waals forces. It's just a small little thing that this is temporary. Want to express this is very temporary. It's just for a moment. It's just like as long as this magnet exists. The moment I take the magnet away, it goes back to how it was. So say we have an example with a bunch of these. What happens? Say I put this magnet next to this what is a non-polar chain, carbon chain, and I have that density go towards the magnet. Now I have this exposed side, right? And now of positive stuff, and say that you have another fatty tail that's right next to it, it's going to get that. And then it's going to affect the other one, and they're all going to have that for a slight moment, just there, put the magnet, then take it back, and then they have this, and then, they go back to what they were. And the way I like to think of this is kind of, a crowd doing a wave, like in a baseball field, where, everyone, like, as the force is coming through, you put up your arms for a second, you can think of that as you're momentarily, you're positive, you're up in the air and you're happy, and then your arms are back down, you're back to neutral. So that's kind of the idea between these van der Waals forces. But again, just really want to emphasize they're very weak, very small. They're short spurts. They are not long lasting like ionic bonds or hydrogen bonding, covalent bonds for sure. Those are the strong ones that are very hard to break. Okay, so just last time, I know that was a lot to go through. I hope it was helpful for you. If you have any questions, any critiques, any spots you would like me to explain better, please feel free to reach out to me and let me know. I'm more than happy to do another video on it or just talk to you guys one on one. So, whatever is best for you. I know that exam is coming up, so good luck to all you guys. You guys got this. If you made it to the end of the video and you're able to listen to me the whole time, I know it means you care about your grade and stuff. So, you know, kudos to you guys. Keep up the good work. I'm sure that you guys are going to do great. And also, just remember, don't be too discouraged by your first exam score. Yao's class, she has a lot of opportunity for just kind of even credit and like equal opportunities to do things with both the homework and the achieve and keeping up with that stuff. And there are some opportunities for extra credit that come along too. So just don't feel too discouraged. This is your first time. This is your first bio test. This might be a whole new world for you, and it's gonna be okay. Just again, as long as you stick with it, I promise you, it eventually starts to make sense. If I could understand it, I promise you that all of you guys can too. So, all right, good luck, guys. You got this.